Okay, great. So I'm going to talk about data science learnings from the airline industry. I was asked to talk about an industry, that you guys might not be so familiar with. So not, medtech or any medical industry, but rather some industry that's maybe more advanced when it comes to these things, right? And the airline industry is one of the sort of pioneers has been one of the pioneers historically of all things analytics, and I find it really interesting. So let's see what we can learn from airlines. Very briefly about myself. I'm Henrik, like I said, I'm a senior data scientist at BCG Gamma. I studied at KTH in Stockholm. I have a master's in mathematics. And I've done a bunch of different things in different industries within analytics at BCG Gamma. Right now, I focus on a lot on climate analytics, and especially within agriculture. So things like how can we, use analytics to solve the food crisis or improve agriculture to sort of sequester more carbon in soils, things like this. But the agriculture sector is certainly not, one of these advanced industries when it comes to analytics. So it's not, particularly interesting to talk about, about finding really advanced and cutting edge solutions in analytics. So instead, let's talk about airlines. But yeah, and again, if you have any questions at all, just feel free to interrupt me or type them in the chat. So we're going to talk about something called mathematical optimization. It's one of the subfields of what we call data science. The most sort of well-known when people talk about data science, often people associate it with machine learning, or when people talk about AI, they think you talk about machine learning. There's many other things within data science that are very interesting and technical as well. One of them is optimization, and there's a lot of overlap between optimization and machine learning. But we're going to talk specifically about optimization. Hopefully, this is a topic that nobody else has spoken about this today in your Big Data Day. So we're going to talk about that, and then we'll talk very briefly about airline operations, and then we'll do a case example of when we applied analytics to solve some problems in airline operations. Okay, so starting with mathematical optimization. So I talked about this. Why optimization, right? So it's one of these like really technical and interesting fields that when you talk about data science, it's so easy to get into machine learning. Machine learning relies a lot on optimization, but optimization in itself is a very interesting problem and topic, and you can solve very interesting problems without using machine learning in optimization. So let's have a crash course in optimization. So the most simple type of optimization problem is called a linear program. And optimization problems are often called programs. And it's a bit of a weird term nowadays, because when we talk about programs, what you associate a program with is sort of programming, a programming language like Python or Java or something like that. And you think about code. A linear program or a program in optimization is not code per se. It's a formulation of an optimization problem in text or in mathematical language. But when they came up with these terminologies, this was a long time ago, and programming was not what it is today. And so we still call them programs. And in a program, optimization program, you have something called an objective function. In this case, our function is x plus y. So x and y are two numbers, and our objective is to minimize x plus y. So minimize the sum of x and y by choosing the values of x and y. And x and y are called our decision variables. These are the sort of levers that we can pull to try and find the minimum to this function. Now, before we're allowed to do this, there are some constraints that we also have that we need to consider. So we say that we're going to minimize x plus y, but it's subject to a series of constraints. So here we say that if we take 1.5 times x plus 2y, that has to be greater than 40. If this is less than 40, then this is no longer a feasible solution to our optimization problem. So this cannot be violated. And then we'll say that 3x plus y has to be less than 100. X has to be greater than 30. And y has to be less than 8. So in order for a solution to be feasible, it has to satisfy all of these constraints. And we want to find the solution, so that the choice of x and y that satisfies all of these constraints, and where the sum of x and y is minimal. Now, why is this called a linear program? Well, it's called a linear program because everything here is linear. And what linear means is that essentially we don't have any multiplications of x's and y's, right? So if you look at all of the x's and y's, they're all separate, right? So we have x plus y, right? X plus y, x plus y. There's x on its own and y on its own. If we had something like x squared or x cubed or x times y or x divided by y, then it wouldn't be linear anymore. But because this is linear, it has a lot of nice properties. And one of them is that linear programs have a sort of very intuitive geometric representation. So all of these constraints are essentially lines that you can draw in a coordinate system. So if we have this coordinate system where x is on the x-axis and y is on the y-axis, then each one of these lines corresponds to one of our constraints. So for instance, x has to be greater than 30. That says that, you know, if we draw this line at x equal to 30, then we know that x has to be greater than 30, so it has to be on the right side of the red line, which is where x is greater than 30. So all of these lines then sort of define this area, which is surrounded by all of the lines, this green area. And this is our feasible space. So all of the points within this green space here will satisfy all of these constraints. So that's the area that we need to look within to find the solution to our linear program. Now, so where is the solution? Well, our objective function here is x plus y. So when is x plus y small? Because we're trying to minimize. Well, x plus y is small if x and y are small. And x and y are small if we go towards the sort of bottom left corner here, because x gets smaller if we go to the left and y gets smaller if we go down. So the optimal solution is here at x equal to 30 and y equal to minus 2.5. So it's right where the red line and this dark blue line intersect. And there's actually, it's not a coincidence that the solution happened to be in an intersection of two lines. There's a really beautiful theorem that says that any linear program will have its optimal solution at one point where these lines intersect. So all of this area in the middle, we don't really need to consider in order to find the optimal solution, or one of the optimal solutions. There can be more than one. We just have to look at the intersections. And that's a lot less points to consider than if we had to consider the sort of infinite number of points that are in this green area. So that's a nice property of linear programs. Let's talk about another class of programs called integer programs. So what's an integer? An integer are whole numbers, right? So not decimal numbers. So integers are things like 1, 2, 3, 4, etc. No decimals. So what if we add the constraint to our program that x and y have to be integers? Well, first of all, we can see that, you know, this optimal solution to the linear program is no longer a feasible solution. Why not? Because y equal to minus 2.5 is not an integer, because it's a decimal number. So instead, the optimal solution is very, very close to what we had before, but it's x equal to 31 and y equal to minus 3, which are integers. In practice, I mean, this is a very simple example. You could solve this by hand easily. In practice, typically you have many, many more decision variables than 2. We just had x and y. You can have essentially an infinite number of decision variables, and you can have an infinite number of constraints as well. Or, you know, if it's not infinite, it can be very, very large. So far beyond what you could do by hand. And in that case, we need computers, and we need big data, and we need all these fancy analytics to help us solve these types of problems.
Can I, a quick question?
Yes.
The final solution after you added the last constraint, that was one of the 4 points.
True. Yes. When we added the integer constraints, then this theorem that the solution has to be in one of the intersections no longer applies. So that only applies when x and y can be sort of any continuous decimal number.
And then the solution would be on some kind of integer matrix within the green zone.
Yes, exactly, right. So we can only, so there's still a finite number of possible points, right? In this case, it's very easy, right? We could draw this grid of integers, and it would be, I don't know, maybe there's like 20 or 30 different options to consider, and we could look at all of them and you just check which one is the smallest. But again, in reality, this will not be a two-dimensional grid. It will be, maybe it's a 2 billion dimensional grid because we have so many decision variables to consider. But yeah, that's a good point.
That's funny how you add a constraint and make the solution harder to find.
Yes.
Or more complicated.
Yeah. So that's a great segue to this point, right? So linear programs are easy. And they're easy because of this theorem that I talked about. So we have an algorithm that we can use to solve any linear program. So irrespective of how complicated the linear program is, if we have a big enough computer, a powerful enough computer, we can find a solution to the linear program in a reasonable amount of time. Integer programs, right? There are fewer integers than there are decimal numbers. So you'd think that integer programs should be easier to solve than linear programs because there are fewer solutions to consider. But that's not true. Integer programs are a lot harder. In fact, they belong to a class of problems in computer science called NP hard. They're really, really hard to solve. And of course, this integer program here is not very hard, right? We can enumerate all of the possible solutions and just check. But in general, integer programs are very, very hard. And there's no algorithm that will solve any integer program. It's an open research problem. But there are a lot of classes of integer programs where we have algorithms that can help us solve the program or find maybe a solution that isn't optimal, but is very close to being optimal. And maybe just to give you some intuition to why integer programs are harder to solve than linear programs. If you imagine we have a speaker and we want to turn the volume knob to find sort of the optimal volume that we want to have for the music that's playing. If you have on the left, representing the linear program where we have a volume knob that has, a sort of continuous dial, we can turn it to any setting between minimum and maximum. It just sort of gradually increases the volume when we turn the dial. It's very easy to find the right setting. We just keep turning the volume knob until we reach the best setting. Whereas on the right, if you imagine you have a volume knob that has only a few settings, and every time you turn it, it jumps to the next setting, and there's sort of a jump in the volume output. If you turn that, and let's say you turn to setting 3 and it's still too low, and then you turn to 4 and it's too high, so you have to go back and compare 3 and 4 and say which one was really the best one between 3 and 4. And that's a lot harder to do. And especially in an optimization problem where you imagine you have, instead of just one volume knob to turn, maybe you have 100,000 knobs to turn at the same time, then it's just easier if they're all continuous. Okay, final point on integer programs. In practice, well, this was quite easy to solve because the optimal solution was very similar to the solution of the linear program. In practice, often the integer decision variables are binary, so they're 0 or 1. And then, you know, in the linear program version of the program, maybe the optimal solution is 0.5. You can only choose between 0 and 1, and then it's not really close to what you had before. So that also makes it a lot harder to solve integer programs. Okay, cool. Let's talk very briefly about the airline industry, so something completely different. So airlines have historically been pioneers in analytics. So for instance, something called revenue management was invented at British Airways in the 60s, I think, which is the revenue management is how do you set prices for the seats in your airline, given that maybe you've sold 30% of your seats and there's 2 months left until the day of the flight. What should the price be for each seat? And what should it be tomorrow? And how does the price change if we sell another 10% of our seats? It's a very interesting problem, and it was solved by, or it was first sort of studied by engineers at these airline firms. And why is that? Well, airlines typically sort of operate at very thin margins, and it's in their interest to solve these types of problems to outcompete their competitors. But there's a lot of room to improve still. Today you can go to many airlines and you'll find that the way they make decisions on which aircraft to delay or cancel on the day that the airplanes are flying, is just some person sitting in front of a giant screen, clicking at things and, you know, like click, delay, click, cancel, you know, just making decisions on a whim based on their experience, which can work, but typically this is extremely complex and it's something where analytics can help a lot. I'm not going to talk too much about this, but very briefly, when you talk about airline operations, there's a whole, you know, a super complex network of tasks that, you know, you have to solve to operate your airline. You have your fleet of aircraft and, you know, which aircraft should fly which route. You have your flight crew, so the pilots and the cabin crew. They all have to be assigned to each aircraft in each flight. You have your ground crew on the airport that also needs to be assigned in a proper way. And then you have the communications to the passengers. And we're going to deep dive into one such problem that the airlines have to tackle. And that's on the day, what's called a day of operations. So the day when the flight is to take off. So let's look at what happens if there's a disruption in a schedule. So we have an airline. Let's take an example airline. They have 160 aircraft in their fleet. There's 30,000 connections every day and 100,000 passengers every day for this airline. So typically, or every day, at the start of the day, they have, you know, their schedule that they've set before. Here's all of the routes that are to be flown this day, the passengers that are going on each flight, which aircraft should be flown for each route, the crew that's assigned to each craft, etc., etc. And there are many things that can happen that derail the schedule, right? So your aircraft have maintenance, and sometimes maybe the maintenance takes longer than expected, or the aircraft has to be taken in for unexpected maintenance. Maybe you hit a bird flying into the airport. There's the crew that could, you know, maybe one of your pilots is sick, or just maybe your cabin crew had a previous delay and now they're not in time to fly the next leg of their schedule. The airports, so you don't operate in isolation typically. You have a lot of other airlines flying from the same airport, and so your schedule is dependent on the airport's ability to meet demand. And your passengers, maybe there's a passenger that's slow to board or doesn't show up for the flight. And this can generate enormous costs for the airline. Maybe you have to cancel or delay some of your flights. And maybe your passengers, maybe they miss a flight, and then that causes them to miss their connection. And for a lot of airlines operate in a model where typically they have a single hub, so a single airport that all of their flights either fly to or fly from. And then the shorter flights are called feeders. And the job of these flights are to feed people into your hub for the longer flight. So they connect to a longer flight. So for instance, maybe you're flying to New York from Stockholm, and you first fly to Copenhagen, and then you have a connection to New York. And in that case, if your Copenhagen flight is delayed, then maybe you miss the New York flight, and the New York flight is where the airline makes the most money. So you really, really want to make sure that if you delay your flights, that connections aren't missed to long-haul flights. So let's look at this. You have a feasible schedule, and then something happened. There's a disruption, and your schedule can no longer work. There's going to be an overlap or a pilot missing or something that is just making the schedule infeasible. So BCG Gamma has a tool that solves this type of problem. It's called Sentry. And essentially, the objective of the Sentry model is to solve these types of disruptions at a minimum cost to the airline, and to do it very fast, right? So this is on the day of operations, and you have to find a way to solve these crises very, very fast. So what can you do when you have a disruption? Well, you can delay or cancel flights, or you can swap two aircraft between two routes, or swap pilots, or swap crew, or make some sort of swap to make the schedule easier to fly. And you have a bunch of constraints, right? So there's a runway that has a certain capacity. You have airplane-specific constraints. So for instance, maybe you're flying to an airport that has very specific requirements on which types of aircraft can land there. Or maybe your aircraft has a maximum loading capacity and you need to make sure you don't violate that. You have your crew availability. So the crew has to have a certain set amount of rest in between when they fly. And you have to allow for a certain time buffer in between flights. So obviously an airplane cannot land and then immediately take off again. They need to have some time in between. And then you have day of operation specific things like maybe there's really rough weather, or there's parts of the airport that's closed down. So you pull in all kinds of live data feeds on, you know, what's the runway situation right now? What's my maintenance situation for my different aircraft? What are my crew? What's the availability of crew, and when do they have to rest? What's the cost of each flight that I'm flying? Maybe one of the flights is fully booked, and so if I cancel that, there's a huge cost compared to another flight that's maybe only 10% booked. Okay, so if it wasn't clear, this is an optimization problem, right? So our objective function is to solve this at a minimum cost, and our decision variables are, you know, delaying and canceling flights or swapping aircraft, and the constraints are all of these things that I mentioned. So you can formulate this as an optimization problem, and it's an integer optimization problem. And I'm not going to get, you know, too deep into the mathematics, but, you know, let's just look at this really quick. This is our objective function, so it's a big sum of different things. And these x's are our decision variables. And essentially this x corresponds to one specific choice of a specific aircraft flying a specific route at a specific time with a specific crew. And if we choose that, then we give it the value 1. And if we don't choose it, we give it the value 0. And if we choose to fly that specific combination, it has a certain cost, which is essentially the fuel cost of flying that route. And then we can also choose to delay each flight. So there's a second set of decision variables called Z, They're also binary, and if you cancel the flight, it has a cost C. There are, which I probably don't have time to go through, we have a whole bunch of constraints, and this is really the bulk of the work of working on these types of optimization problems. Is you have all these constraints that you understand sort of what they mean in terms of, you know, the actual operations, but you need to formulate them in a mathematical or programming language for your optimization solver to understand them. So there's a big piece of work of just formulating, you know, what does it mean that an aircraft has to be on the ground for a certain amount of time before it can take off again? How do we formulate that in mathematics? So when Sentry solves these types of problems, there's a huge number of possible ways to configure this. So typically there can be something like 2 to the power 40,000 possible solutions to consider. And is that a big number? Yes, it's a very big number. The number of particles in the observable universe is much, much smaller. So I think final thing I have time to go through is just a quick example here of Sentry solving a problem like this. So this is a flight schedule. We have each row here corresponds to one aircraft, and each one of these boxes is a flight. So for instance, this is a Manchester flight, and then it's another Manchester flight of the same aircraft flying back to the original hub. So there's a problem here. This Manchester flight has been delayed, and it's going to cause the aircraft to come in too late to be able to fly this Helsinki flight. So the Helsinki flight is going to be delayed as well if you don't change something. And there's another delay to this Copenhagen flight, and it's going to delay this Prague flight. And if this Prague flight gets delayed, then there's another delay in this Hamburg flight, and potentially we might even have to delay the Copenhagen flight in the evening. So how do we solve this? Well, what Sentry does, it's going to see that, you know, hey, there's a small buffer here between this flight and the Zurich flight. And if this Prague flight is delayed, then this Zurich flight will still be able to fly. So if we swap the Zurich and the Hamburg flight between the two aircraft, like you see here, then this aircraft can still fly the Zurich flight, and this middle aircraft can fly the Hamburg flight. But if we do that, then the Zurich flight is going to overlap with the Copenhagen flight that was for the evening. So we can swap the Copenhagen flight up to the first aircraft, because that can still fly the Copenhagen flight, and the final aircraft will fly this Manchester flight in the evening. So this was quite simple. I mean, there's only 3 aircraft, and you know, you could probably do this. A person could do this quite easily, but in a real airline, there's many, many more flights and many, many more aircraft, and it gets very, very complicated. Here's a much bigger example, and Sentry solves this by making 62 swaps between different aircraft, and it only takes 2 minutes to do it. And that's probably time. So I don't know if there were any questions in the chat. I'm not sure if I have time to answer any, but I hope you found this interesting. And yeah, I don't know if I have time to answer questions, but I'll leave it over to Jing and Frederick.
Sure. Thank you so much, Henrik. We have a couple minutes to take questions. The next speaker is running a bit late.
Okay.
If you have time, Henrik.
Yeah, I have a few minutes for sure.
We have a question from Eric. I can see Eric Sachs.
So this is super interesting. But it's pretty easy to see a likeness to an operating schedule or use of operating rooms and personnel. In my own work, we sometimes have to coordinate all the operating rooms and personnel, and people get delayed, which is a pain in the ass. Is there? It's obviously a lot less complex, but is there like a solution developed for that kind of scenario?
You're right. I hadn't even thought about that. That's a very similar type of thing, and I'm sure there are many products on the market. I mean, we don't really sell products in the sense that, sure, this has a name, but you know, it all gets like configured specifically to the airline that we work with, and this could easily be, you would solve the problem you talk about using exactly the same types of techniques. So yeah, that'd be a very interesting use case.
Do you have any more questions from the audience? I think for me, one of the most interesting parts of this was, I think the way we approach it in healthcare, like Eric just said, is when you have very complicated problems, usually you throw more people at it. Usually you create, large support staff structures to deal with these kinds of logistical problems. Maybe not even just for operating rooms, but just like scheduling. How do you, schedule staffing for a hospital of 8,000 people where somebody needs to take care of the kid and somebody gets sick? And so it's really interesting and inspiring to see how you've solved it and scaled this in a business where you need this to happen quickly, and there's a lot of people's travel itineraries and money at stake. And I think that's it's incredibly inspiring to see how forward-looking these industries have been, and maybe we can get inspired from them in the healthcare industries as well.
Sure. Yeah.
Do we have any last questions for Henrik from the audience?
I guess not.
All right. Well,
all right.
Thank you so much for taking time from your busy schedule to come talk to us. It's always really inspiring for us to hear insights from other industries, and I hope you'd be interested in come back sometime.
Sure. Yeah. Thanks for having me, and enjoy the rest of your talks. I'm sure they'll be very interesting.
Great. Thank you so much, Henrik.
Bye bye.
Take care.